In the first part of 4.5, we determined whether a function is increasing, decreasing, or concave up, concave down by using tangent lines. In the second part, we are going to be using calculus in order to find inflection points and determine when a function is concave up or concave down using the second derivative. So remember that inflection points are where the second derivative is equal to 0 or when it's undefined. So first, let's just find the second derivative. Now, we're going to be using the power rule, and I'm not going to spend too much time since we've done this before many times, but we have 5 times 12 is 60x to the fourth, 4 times 60, so on and so forth. For the second derivative, 4 times 60 is 240x cubed, 3 times 240 is 720x squared, 2 times negative 300 is negative 600x. That is the second derivative. Now, the second derivative cannot be undefined. We can only have undefined values when you have a denominator, which in this case we don't. So because it cannot be undefined, we're going to take a look at where the second derivative is equal to 0. So we take our second derivative, set it equal to 0. Remember, anytime they have a common factor, like in this case, they have a common factor of 240, it's always easier to factor it out. So we get x cubed plus 3x squared minus 2.5x. And now they all have a common factor of x, so I can factor that out. So I have x times x squared plus 3x minus 5. From here, we can use the quadratic formula to solve the equation x squared plus 3x minus 2.5. And I'm not going to go to the quadratic formula. It is a prerequisite to this class, so if you forgot how to do the quadratic formula, please go to YouTube. And there are a million lessons on the quadratic formula. But when we do that, we're going to have from this x squared plus 3x minus 5, our solutions are 0.6794 and negative 3.6795. And then for x, you just set x equal to 0 by the zero product property. So our three solutions are 0, 0.6794, and negative 3.6795. Once we have these are going to be the inflection points because this is where the second derivative is equal to 0. Once we have those, we are going to make our intervals. So go in the order of the number lines. So you have negative 3.6795 and then a 0, then a 0.6794. And our intervals are going to be from negative infinity to negative 3.6795, and then from negative 3.6795 to 0, 0 to 0.6794, and then 0.6794 to infinity. Right, and I can shade these in for a better visual. Interval 2, this is going to be interval 3, and then we have interval 4. So we have to pick a test point in each of the intervals, okay? So you can pick anything to the left of negative 3.6795, I pick negative 4. Pick anything between negative 3.6795 and 0, I pick negative 2. Anything between 0 and 0.6794, I picked 0.5. And then anything to the right of 0.6794, I picked 1. Now remember, the second derivative tells us if the function is concave up or down. So in the second derivative, not the first, not the original function, in the second derivative and the original function, not the simplified one, we're going to plug in all these values of x, negative 4, negative 2, 0.5, and 1. Those are our test points. So just use like Desmos.com or Scientific Calculator, plug them in, and we get negative, positive, negative, positive. So anywhere where it's negative, it's concave down. Anywhere it's positive, it's going to be concave up. Okay, next example. We have our function 2x plus 6 over 4x plus 1. And let's just take these like one by one. So the first part says, consider this function. For this function, there are two important intervals, negative infinity comma a and a comma infinity, where the function is not defined at a. So we want to figure out where is this function undefined. And this function is going to be undefined where the denominator is equal to 0. So if I set the denominator 4x plus 1 equal to 0, I get x equals to negative 1/4. That is where it's undefined. The second part says for each of the following, determine whether the function is increasing or decreasing. So increasing, decreasing, that depends on the first derivative. So our function is f of x equals to 2x plus 6 over 4x plus 1. And if I want to take the first derivative, I have to use the quotient rule because we're dividing. So my a is going to be 2x plus 6, and my a prime is 2. My b is 4x plus 1, and my b prime is 4. From here, I'm going to take a prime times b minus b prime times a all over b squared. So if I do that, my a prime is 2 times 4x plus 1, which is my b, minus my b prime, which is 4, times 2x plus 6, which is my a. I distribute and I simplify, and I get negative 22 over 4x plus 1 squared. That is going to be my first derivative. Okay, now I want to know where is this increasing or decreasing. So I'm going to make two intervals. Remember, negative 1/4. This is going to be where the function is undefined. So my two intervals are going to be negative infinity comma negative 1/4 and negative 1/4 comma infinity. So if I'm looking for increasing, decreasing, then I'm using my first derivative. So my test value, I can pick anything to the left of negative 1/4, so I pick negative 1. And then for my second test value, I pick anything to the right of negative 1/4, which is going to be, I pick 0, but you could pick any number. And I'm going to plug those in to the first derivative for increasing, decreasing. So if I plug in negative 1 for x in my first derivative, I get a negative answer, negative 22 over 9. And if I plug in my second test point, which is 0, I'm going to get negative 22. So because both of those values are negative, it means that the function is decreasing everywhere. If you were to graph this on Desmos, the function is going to be decreasing everywhere. No, in no interval is the function going to increase. Okay? So it's decreasing on both intervals. And then it says, note that this function has no inflection points, but we can still consider its concavity. For the following intervals, determine whether the function is concave up or concave down. And again, we're looking for this a value of negative 1/4. So from negative infinity comma negative 1/4 and negative 1/4 to infinity, we want to know is the function concave up or concave down. Now concavity depends on the second derivative. So in the next slide, we are going to find the second derivative. So my first derivative is negative 22 over 4x plus 1 to the second power. Now remember that here we're not going to be using the quotient rule because the numerator is a constant. It's not a variable like in the previous problem. So I'm going to remind myself of the rules of derivatives. Anytime you have a constant on the numerator and a variable on the denominator, that variable needs to move up to the numerator. So you know what, actually, I did this using the quotient rule, so I'm just going to do that. I'm sorry. But you could have also done it the other way where you move this to the numerator and then take the derivative that way. I can show you guys that as well. So our a is going to be the numerator, negative 22, and the derivative of any constant is 0, so a prime is 0. Our b is going to be 4x plus 1 to the second power. For our b prime, the 2 is going to come down, so we have 2 times 4x plus 1. But anytime the parentheses contains anything that's not x, any other function, we have to multiply by the derivative of the parentheses, which is 4. So 2 times 4 is going to be 8 times 4x plus 1. And then for f double prime of x, if you do use a quotient rule, which you can do, it's going to be a prime b minus b prime a all over b squared. So a prime is 0. So we have 0 times 4x plus 1 squared, which is your b, minus our b prime, which is 8 times 4x plus 1 times a, which is negative 22. All of that divided by b squared. So that'll be 176 times 4x plus 1. You have negative 8 times negative 22. That's a 176. We distribute that and you get 704 plus 176 all over 4x plus 1 to the fourth power. Why is it to the fourth power? Because remember, it's a denominator squared. So if we take the 4x plus 1 to the second power and we square it, because we're squaring the b, if you square this, it'll give you the fourth power. All right, so once we have this, this is our second derivative, and our interval is going to be the same. negative infinity comma negative 1/4, negative 1/4 comma infinity. We have the same test points, which are negative 1 and 0. But now we're going to plug them into the second derivative, not the first, but the second derivative for the test of concavity. So if you plug in f of negative 1 into the second derivative, just use Desmos or whatever, we get a negative value. If you plug in the second test point 0, we get a positive value. So it's concave down on this first interval, and it is concave up on the second interval. And we can check this during class. All right, the next example, we have 2x plus 2x plus 6x to the negative first power. It says here there are 4 important intervals, negative infinity a, b, b, c, c, a, where a and c are the critical numbers, and the function is not defined at b. All right, so let's go ahead and break this down. So f of x is going to be 2x, and 6x to the negative first is same as 6 over x. So first off, we want to know where is it undefined? Well, it's undefined whenever the denominator is equal to 0. So x equals to 0 makes f of x undefined. So the b value is where the function is not defined. So the b value is going to be 0. Okay, now we got to find a and c. A and c are the critical numbers. Now, if you recall from the previous section, critical numbers are numbers where the first derivative is equal to 0, or undefined, but we already found the undefined. That's x equal to 0. So let's find the first derivative. Okay, our first derivative for 2x, there's a 1 here. 1 times 2 is 2, and the x goes away, so it's just going to be 2. For 6x to the negative first, you multiply negative 1 by 6, that's negative 6, and subtract 1. That's going to be a negative 6x to the negative second power. And then the x to the negative second, we can't have negative exponents in our final answer, so it goes to the denominator, and we get 2 minus 6 over x squared. This is going to become the first derivative. Now, the critical value is where the first derivative is 0 or undefined. We already know it's going to be undefined at x equal to 0. So now let's find the critical numbers. The critical numbers is where this function, 2 minus 6 over x squared, is equal to 0. So I'm going to set it equal to 0. And let's do a little bit of algebra. So whenever you want to solve an equation, you have to separate the numbers and the variables. So I'm going to subtract 2 from each side. We get negative 2 equals to negative 6 over x squared. But the x squared has to be on the numerator. So think of it like negative 2 over 1. And a shortcut is we can just cross multiply. So the negative the x squared goes to the numerator, and the negative 2 goes to the denominator. So if you divide both sides by negative 2, we get x squared equals to 3. So we cross multiply it, we divide it by negative 2, we get x squared equal to 3. If you square root that, we're going to get x equals to plus or minus radical 3, which is 1.7321. So those are going to be our critical numbers, and we already know it's undefined at 0. So we found the first derivative, we set it equal to 0, solve for x. So our critical numbers are negative 1.37321, 0, and 1.7321. We can make intervals and then pick a test point on each interval. So to the left of negative 1.7321, I pick negative 2. In between, I pick negative 1. Between 0 and 1.7321, I pick 1. To the right of 1.7321, I pick 2. Okay, now we got to figure out what is the sign of f double prime of x. So take each of these test points and plug them into the second derivative. Okay. I'm sorry, we're still doing the first part. So increasing, decreasing means the first derivative. So this should say f prime of x because we're looking for the first derivative, not the second. I apologize. So in the first derivative, if I plug these test points in, I get positive, negative, negative, positive. So it's going to be increasing, decreasing, decreasing, increasing. So once again, I pick my test points and I plug them in to the first derivative, which is here. This is my first derivative. And this tells me if the function is increasing or decreasing. Now, I'm going to put up the work for the second derivative test, and I want you to copy this down. Come prepared to class having it copied down, and I'll explain it during class. Okay, so just copy this down, And in class, we'll talk about the second derivative.